Now we'll introduce the big formula for determinants. I have written out the formula. I understand that it is not easy to follow, so let's just read along. The formula says that the determinant of A is the sum over all n factorial column permutations. So what does this n mean? It means the matrix, or where does it come from? The matrix is n by n. Okay, we are assuming that A is n by n. And we are summing over all n factorial column permutations. So when you look at this, it's a rearrangement of the identity matrix, of the columns of the identity matrix. So for example, if I have 3, 2, 1 for a 3 by 3 case, it means that the third column of the identity matrix is a first column in P, that the second column continues to be second column, and that the first column of the identity matrix is the third column of P. So that's what P represents. It's just a short way of writing where the columns of the identity matrix have gone. So the first column has gone into alpha, the alpha column has gone into the first column, the beta column has gone into the second column, the omega column has gone into the nth column position, and omega could mean anything. So these will be numbers. These will tell us which column of the identity matrix is first, which is second, and so on. Now, this permutation matrix, we know, has a determinant either +1 or -1. Okay, and we can compute it by trying to get back to the identity matrix. And so attempting to go back to the identity matrix would require column exchanges. By the way, row exchanges or column exchanges, when it comes to finding the determinant, both work in the same way, and that is because we have that the determinant of A equals the determinant of A transpose. So this equation tells us that all operations that we can do on the rows of A, we can also do them on the columns of A, because the columns of A are the rows of A transpose. So row exchanges produce a negative sign in the determinant. Similarly, column exchanges produce a negative sign in the determinant. If you have two rows or multiples of each other, the determinant is 0. Similarly, if two columns are multiples of each other, the determinant is 0, because you can interpret column operations as row operations on A transpose. All right. Now, what are these A's in the formula? These are the entries of the matrix A. So this is the entry in the first row, but alpha column. This one is the second row, but beta column. This one is the nth row, but omega column. So you see, this says sum over all permutations P. So this P tells us from which column. So alpha, beta, omega, you see them here. So the first one is for the first row and alpha column. Then this beta says take a term from the second row and beta column. And this term says take an element from the nth row and the omega column. And we have n factorial different permutations of size n by n. And so this sum will have n factorial many distinct terms. Okay. As you can imagine, the way n factorial works, so 1 factorial is 1. Okay, that's great. That just says if you have a matrix with only one entry, then the determinant is that entry. Then 2 factorial is just 2. So this seems like, okay, there will be 2 terms in the sum. There will be something plus something. Then if you look at 3 factorial is 6. That's 3 times 2. 6 is still a manageable number. 6 terms in the sum. But as soon as you go to 4 factorial, that's 24. Going to 5 factorial, that's 5 times 24. That is a very big number. So this formula is not effective beyond size 3 by 3 matrix. Nonetheless, it's important to understand. Okay, so let's apply this formula on a 2 by 2 matrix so that we can understand what that means. So here's a general 2 by 2 matrix, A, B, C, D. When I use these vertical lines, I'm actually referring to its determinant. Now, we have 2 permutations, so there are only 2 columns. We could either choose them the same way, or we can choose them in the opposite way. So I could either do 1, 2, so the permutation could be 1, 2, which exactly means take the identity matrix, or the permutation could be 2, 1. That's it. 2 numbers can only be arranged in so many ways. So 1, 2 means take the first column of the identity matrix and place it as the first column in this matrix P. And then 2 says take the second column of the identity matrix and place it as the second component because you have first and second. So this matrix really is just 1, 1. And the other one is 1, 1 like this, right? This is the second column of the identity matrix placed in the first position. And this is the first column of the identity matrix placed in the second position. And so the formula continues to say that the determinant of the matrix A, B, C, D is the determinant of this first permutation 1, 2. So the determinant of this matrix, which is the identity, times. Then it says take 1 alpha. Alpha is 1. So take A1, 1. A1, 1 in this case is just A. And maybe I should do it like that because this might be confusing. So let me say A1, 1, A1, 2, A2, 1, A2, 2. Okay, so reading the formula, alpha is 1. So I should have 1, 1 here. And then beta is 2, so I should have A2, 2. For the first permutation, okay, I have P1 if you like, P2, okay? Even though we would normally write them P1, 2, P2, 1, so that we can summarize what's going on, but it doesn't matter. Plus the determinant of the other permutation and it's alpha beta. So now here this is alpha, this is beta, this was alpha, this was beta. So alpha and beta have changed values. We have A1, 2, and then we have A2, 1. And that's it. We have a formula for the determinant of the 2 by 2 matrix. Now all that's left is for us to compute the value of the determinant of the permutation. The determinant of the identity matrix is simply 1, so that first part of the sum is A1, 1, A2, 2. And the second determinant, this one, is actually -1 because it represents a single row exchange. If we exchange the rows once or the columns, doesn't matter, we're going to go back to the identity matrix, but each row exchange or each column exchange changes the sign. So in fact, we have minus A1, 2, A2, 1. Okay, I will summarize this on a formula that has A, B, C, D because it's a little bit easier to see. So we have A, B, C, D. You can think of it, take terms along this diagonal with a plus sign, terms along this diagonal with a minus sign. And your formula becomes AD minus BC. For a 2 by 2 matrix, I do encourage you to use this formula. It's very easy, but pay attention to the fact that it doesn't generalize. So this only works for a 2 by 2 matrix. Now, I think the 2 by 2 case is very revealing to explain where this formula actually comes from. So far, I've only given you the formula, assuming it is true, and said, okay, this is how you can apply the formula. Now, let's look at the 2 by 2 example a little further and see how it comes from the 3 rules, the first 3 rules that define the determinant for us. So if I look at the matrix A, B, C, D, remember that we have linearity. So I can write the first row, AB, as a sum, A0 plus 0B. Linearity in the first row says that I can write this determinant as a sum of 2 determinants, A0CD plus 0BCD. This is linearity in the first row. Now, I can use, on each of these matrices, I can use linearity in the second row. Now, the second row, CD, is the sum of C0 plus 0D. I can do that. So, from the first matrix, from the first determinant, this one, I will get two matrices because I will have, or 2 determinants because the second row splits. And then from this, I will get 2 more. So the first 2 will be A0 and then C0 plus A0 and then 0D. Okay, that's from the first matrix. I'll maybe put parentheses. Plus, from the second one, similarly, I have 0B, so the first row stays unchanged in both of these. Okay. And the second rows better add up to CD, so I could have C0 and then 0D. Now, you have a column of zeros in the first determinant. That tells you that the determinant is 0. Also, the column of zeros says that the second row is a multiple of the first, which again tells you that the determinant is 0. And the last matrix also has a determinant equal to 0. So what we see here is that these are all the ways in which we can choose exactly 2 terms from, or rather not, maybe I say it differently. If you are allowed to take 1 term from each row and write that determinant, then these are the 4 possibilities. You could take A from the first row and then C or D from the second. So that's given in these matrices. So if you take A from the first row and then you can take C or you can take D. The problem when you take C is that you have 2 rows that are multiples of each other and you get a determinant 0. And the reason for that is that A and C actually come from the same column. So choosing from the first row in this formula says you cannot choose from the first column anymore. You've sort of taken from that column. So the choices that survive, these choices are obtained in the following way. Take exactly 1 term from each row and each column. So if I have taken A, then I cannot take B and I cannot take C anymore. I'm left with D. So that's this choice. Okay, now I've taken care of what I can do if I take A. Now what if I take B? Well, I cannot take the first row and I cannot take the second column, so I'm left with C. Because if I take D, I get multiples. So that is exactly how the formula works, and you will see that repeated in the 3 by 3 case. Okay, so that's exactly how it works, and it comes from linearity. So here again we get that formula. We can factor A and D out, get the identity matrix, then factor B and C out, get the permutation matrix. Okay, let's move to the 3 by 3 case. So now I have A11, A12, A13, A21, A22, A23, A31, A32, A33. So I don't want us looking at the formula, I want us to understand the formula. We will obtain the determinant by making all the possible choices for choosing exactly one term from each row and each column. So let's first choose A11. Okay, that will eliminate the first row and the first column. It means I cannot choose any more from the first row or the first column. So then I'm left with this matrix over here. So what I'm saying is I have a determinant A11, then 0 here, 0 here, 0 here, 0 here. I'm not taking from here. And then I get to choose either A22 or A23. So if I choose A22, then I can no longer choose from the third row, I can no longer choose A32. I have to go to A33. On the other hand, if I were to choose, so still with A11, right? These are not all the choices. So for A11, I could then choose either A22 in the second row, or I could choose A23 in the second row. So then I have A23, and then the third row will force me to choose A22. So one term from each row and one term from each column. I cannot choose two things in the same row or the same column, because that way I will actually get a zero determinant. So these are the two ways in which I can choose A11 in the first row. Now let's say I don't choose A11, I choose A12. I know that I have two choices for the second and third row. So I have it like this. Okay, I have chosen A12. That says don't look at the first row anymore. You're done there. And don't look in that column. So now in the second row, I can either choose A21 or I can choose A23. So let's choose A21 here and A23 there. Now, if I have chosen A12 and I have chosen A21, that means I can no longer look at this. I can no longer look at this, or this, right? Because those are the rows and columns of the two terms. So I'm left with A33. So here I better choose A33. And similarly, if you look at my choices here and here, I'm eliminating this row and that column, this row and that column. I'm left with A31. And finally, oh, I should not have written equal here. That's a plus. Finally, I get to choose A13 from the first row. Now, having chosen A13, I don't look at the first row, I don't look at the third column. Then my choice for the second row is A21, A2, or A22. So I could do A21 or I could do A22. If I have chosen A21, I have to go into the third row and second column, and that is A32. And then here I have A33. Now you see, this is the sum. This is how we compute the determinant. We have a bunch of triangles. There are 6 matrices. Where are the permutation matrices? Well, I could factor these numbers out and I'm left with permutation matrices. What are the permutation matrices? Maybe what I'll do is I'll make this a little bit smaller. There we go. So the permutation matrices, the first one, I can write A11, A22, A33, and then the permutation matrix is just 1, 1, 1. That's the identity, but that is a permutation matrix. Plus the second term is A11, oh, sorry, I have a mistake there. That should be 3, 2. A23, A32, so that's another permutation. And we have 1, 1, 1 for the permutation matrices. plus, so maybe I'll separate these, plus, so you understand, the reason I can pull these numbers is because I have a linearity in each row. I can factor that number out, and I can factor that number out and that number out. And the reason is because I actually have zeros here. So you could say that the first row is A11 times the first row here. The second row is A22 times that second row. And A33 is, or the third row is A33 times this third row. So that's how linearity works, and that's why. So because we have exactly one term chosen in each row, we can factor it out. If we had another number here, then A11 would not just be a common multiple. You're not going to get these permutation matrices. Okay, then we have A12, A21, A33 times 1, 1, 1 plus A12, A23, A31 times 1, 1, 1 plus A13, A21, A32 times 1, 1, 1 plus A13, A22, A33 times 1, 1, 1. Now these permutation matrices have a plus or minus sign, so you understand that the determinant will be these products over here, the sum of these products, but half of them will be with plus sign, half of them will be with a minus sign. How do you know which is which? Well, you just try to compute the determinant of the permutation matrices, namely, how many row exchanges do you need to go back to the identity matrix? If you need only one row exchange, then the permutation sign is minus. But if you need two row exchanges, then the permutation sign is plus. So let's look at the signs. The identity matrix has a determinant plus 1. In the next one, if I just exchange these two rows, I go back to the identity matrix, so I know that the determinant here is negative 1. Then the next one, similarly, if I exchange the first two rows, I get back to the identity, so I know that the determinant here is negative 1. And I know I have 3 positive ones and 3 negative ones. So if I just go to the very last one, I see if I exchange the first and the third rows, I go back to the identity, that's a negative 1. The other two have to be plus 1. So just by elimination, I know I have half of the permutations to be even and half of the permutations to be odd. Of course, you can take your time and check this. Now, I went this long just to explain how the formula works. I'm not going to do that on a 4x4 matrix because then I have 24 terms. I just want to give you a bit of a generalization or how to remember which choice of numbers is positive and which is negative. I don't really want you to. This formula would take too long if you have to compute the different permutations and decide whether they're even or odd. So let me show you another way to write the same formula, and it only works for the 3x3 case. So if I have the matrix A11, A12, A13, A21, A22, A23, A31, A32, A33, what I can do is I can copy the first two rows. So I will do A11, A12, A13, A21, A22, A23. And again, I repeat, this only works for the 3x3 matrix. It does not work for a 4x4. You could also copy the first two columns right here and the same trick will work. I just slide the rows down because I'm going to be writing the answer over here. Just a question of how you want to organize it. Now, I'm going to be looking for diagonals that contain 3 components. So here is one diagonal right here. It should hit 8, 3, 3. Okay, maybe I'll go back if this lets me. Oh, it doesn't. Okay, so you're gonna have to live with that. And then, so that's an arrow in this direction. Then I have another arrow in that direction and another arrow in that direction. This direction is positive. Then I have 3 diagonals in the opposite direction. This is negative, this is negative, and this is negative. So my determinant is the product along the positive sides and then the product along the negative diagonals, if you like. So the first positive diagonal has product A11, A22, A33, plus along the second one, I have A21, A32, A13, plus along the third one, I have A31, A12, A23. And then the other diagonals, they come with minus signs. So I have minus A13, A22, A31, minus A23, A32, A11, minus A33, A12, A21. So I did product here with a positive sign, plus product here because of that positive sign, plus the product here, and then minus the product here, minus the product here, minus the product there. You can confirm that these are exactly the same things, that this is the same formula. And I think that is enough for the big formula.